All right, we have a nice graph here of a velocity. We also have a table showing some values of the velocity over time. And the first question says, during what intervals of time is the acceleration positive? So A of t is going to be the same as v prime t, and this is our graph of v of t. So v prime is just going to represent the slope of v of t. So we can see whenever v of t is increasing, v prime t is going to have to be positive. Whenever v of t is decreasing, v prime t is negative. So what we can do here is use some colors. So we'll start with green for our increase. So this whole time, the slope is positive because v of t is increasing. Boom. And then it starts to decrease. So now v prime is negative, but then it goes positive again right here. So this is where v prime is positive. So let's just read those intervals off. Looks like we're going from 0 until 35. Okay, I kind of overlapped there, but that's the top there at t equals 35. Just really double check. Yep, okay. So v prime t positive from, we can use this format. We'll say 0 less than or equal to t less than, I don't like this. Okay, from t equals 0 to t equals 35. Okay, and it looks like we're also from t equals 45 to t equals 50. And then we can say because v of t is increasing on those intervals, and we have to provide that justification to be safe. Because it says give a reason for your answer. So it's not enough just to have the intervals. I'm guessing that the intervals themselves are 1 point and the justification is another point. Okay, find the average acceleration over the interval 0 to 50. So let's go to a new window here. And we have a table that's telling us our velocity at all these different times, right? And the average acceleration is just going to be the average rate of change of velocity from 0 to 50. So we're going to do, and we can say we'll say v of 50 minus v of 0, and then we're going to divide that by 50 minus 0. Okay, v of 50 is 72. V of 0 is 0, and we can do that over 50 minus 0. So our final answer is 72 over 50, and then that's going to be in feet per second squared because it's the rate of change of feet per second, the rate of change of velocity. Okay, moving along, find the approximation for the acceleration of the car in feet per second squared at t equals 40. So it's asking us to approximate a prime 40. Okay, let's get our table back in here. So let's see where 40 would be. Oh, well, in fact, we know the velocity at 40. So we can see that it's between 45 and 35, obviously. Okay. So what we can do is use 45 and 35, the average rate of change of the velocity on that interval, and that will help us approximate a prime 40. Because we're looking for the interval that contains 40. So we'll say v of 45 minus v of 35, and then divide that by 45 minus 35. Okay, so then we have a v of 45 is 60. Okay, v of 35 is 81, and then that's going to be divided by 10. Okay, so this is negative 21 over 10 feet per second squared. So that's our approximation for the instantaneous acceleration. I keep getting cut off here and it stops recording, so I really tried to pick up right where it cut off. It was mid-word there. So yeah, this is our approximation for the acceleration at t equals 40. We just took the average acceleration between 35 and 45, and then that's approximating the instantaneous acceleration at 40. Okay, part D. Approximate the integral from 0 to 50 with a Riemann sum using midpoints of 5 subintervals of equal length. Okay, this is just got cut off again. I'm getting very mad at my iPad. We're going to press on here. Okay, so If we're using subintervals of equal length, 5 subintervals, they're going to be in intervals of 10, right? Because if we do 50 divided by 5, we get 10-second intervals. And what we need to do here, because it's a midpoint, is we look at our interval from 0 to 10. And obviously in a left Riemann sum, we would use the y value with 0. In a right Riemann sum, we'd use the y value with 10. But in a midpoint Riemann sum, we're going to use the y value right in the middle. So I have to redraw this. Okay, so we're going to use the y value that goes with 5, right? And that's going to be 12. So our first rectangle is going to have a base of 10 and a height of 12. Okay, go over and look at the picture. So from 0 to 10, that's our interval. We're going to use the y value at 5 to make our rectangle height. So this rectangle has a base of 10 and a height of 12. Okay. From 10 to 20, we're going to use the y value of 15 to make the height of our rectangle. So it has a base of 10 and it has a height of 30, because that is the y value that goes with 15. Right, from 10 to 20, okay, 15 goes with 30. So we're going to do plus 10 times 15, okay, plus 10. Now we're going to use the y value with 25, which is 70, plus 10 times the y value with 35, which is 81, plus 10 times the y value with 45, which is 60. Keep running out of space here. Okay, so now we just need to add these up. This is a calculator allowed question, which means you can just type these in and figure out what you get. So if you were to type this in, you would get, well, actually, first what I want to point out, since our subintervals are equal length, all of our widths are the same, so we could more easily write this as just 10 times 12 plus 15 plus 70 plus 81 plus 60. Okay, and that's going to be 2,530 feet. Okay, that is our Riemann sum approximation. And does it ask for interpretation of what that means? Yeah, explain the meaning of this. Okay, so what that means is that the car has been displaced by 2,530 feet. Okay, this is displacement. Okay, so car's displacement from t equals 0 to t equals 50 is approximately because it's a Riemann sum, 2,530 feet. Note that the PDF answer key says this is an estimate for the distance traveled by the car, but remember the integral of a rate function, velocity, is the net change. So not how far did we go, but how far have we been displaced, our net change of our position. So this is actually an estimate for the car's displacement over the course of that 50-second time period.